Okay, so let's dive into the Euler's identity. So Euler's identity is just this equation. That's it. That's it for this video. Now, we're going to analyze and to see how actually this equation works. First of all, it is considered the most beautiful equation in math. And at the end, we will be checking exactly why this equation is considered like that. But for now, let's analyze the elements of the Euler's identity. First of all, we have the E number, or the Euler's number, which is equal to 2.71828, and it goes on. It has unending digits. Also, having unending digits, it's the pi number, which we know that is the circumference diameter ratio of a circle. And it's equal to 3.14159, and goes on. Then we have the I number, which is equal to the square root of -1. And we know that it's the basic unit of the imaginary numbers. And also we have a 1 and 0. Okay, so the Euler's number. We know that the Euler's number is the base of natural algorithms. And we'll not dive into what this number means, but just to know that it was discovered through the study of compound interest and calculus. And well, here we have to what number is equivalent the Euler's number, but how we calculate the Euler's number. Here we have how we calculate. So if we take 1 plus a fraction of 1 over 1 factorial and then plus 1 over 2 factorial, and we increase the denominator factorial by 1 each time, we get the E number. And this goes to infinity. Each time we add another number, another coefficient of 1 over the next number factorial, we approximate more and more to the actual Euler's number. Okay, here we have it again, the way we calculate the E number. And you agree that this is just equal to E to the first power. But if we want to get a more general approach, it would be more appropriate to write it as e to the x power. And then it's just the same thing, just we change the 1 of the numerator for an x. And every time we increment the power of the x 1 more. So we have that every fraction will have the same number as power of the x and as denominator factorial. And we can express sine of x in a similar way to the E number to the x power. So as we can see, it's plus x over 1 factorial minus x to the third power over 3 factorial plus x to the fifth power over 5 factorial minus x to the 7th power over 7 factorial, and it goes on. It's very similar. The only difference is that we increment, every time we increment 2. And also we alternate the signs, starting from positive. Cosine works in a similar way. The difference is that we put a +1 at the beginning. And also we start from 2. Also, we alternate the signs and we increment by 2, but we start from a negative sign here. And of course, also it goes on and on. So you may think that there's kind of a relationship between cosine, sine, and the E number. Here I put all the equations together and they might seem to match. We may think that in fact sine plus cosine of x it's equal to e of x. And it is almost true, but as we can see highlighted here in the red circles, there are some signs that do not match the e to the x equation. So there's something we can do with this. Okay, so to solve this problem of the signs, it comes to using our I number friend. And we know that I is equal to the square root of -1. But we turn it to the second power, it's just equal to -1. And to the third power, I to the second power times I, and so on. So what we're going to do here to solve the problem of the signs is to just multiply every x term by I. And why we do this? Because I is the only number that multiplied to the second power gave us -1. And then we can get also after doing some simplifications to all the terms, we can get the terms that are required to be negative to be equal to sine plus cosine dx. But we're not done. We're still some things to solve. So now we can identify that we have real and imaginary terms. So here I highlighted in color, so the green are the real and the red are the imaginary. And if we rearrange them to have them together, is where magic is about to happen. Here we have, again, the terms rearranged, but we can appreciate that we can factor the I for the imaginary terms. So, indeed, we factor, and we can appreciate that the real terms, it's nothing but the expression we use to get the cosine of x. And the imaginary terms, it's another thing than the expression to get the sine of x multiplied by I. And this is called the Euler's formula. Boom, magic. Not to confuse with the Euler's identity. They are related, but they are not the same thing. But where's the Euler identity? Okay, so where's Euler identity here? Well, it's no other thing but Euler's formula, the one he saw here, a special case. So instead of having x, we have pi. So we substitute pi, and we know that cosine of pi is equal to -1 and sine of pi is equal to 0, that we can appreciate in these graphs. And we have that. We substitute, as I said. Then now we substitute the equivalences of cosine and sine of pi, and we solve for the zero, and we end up with the Euler's identity. So it's just the same we saw here. Just the same. Okay, so let's go right to the end. And why is the most beautiful equation? Because we have three numbers on totally different math worlds. E, pi, and I. In a just simple equation of 5 terms. Thank you so much for seeing this video. See you on the next one. And here are the references so you can check all the info. Bye.